Good afternoon, everyone. Please take a seat. So, my name is Hannes.
I'm Gabriel.
And we both work for Freeletics. And since you're here today, you totally got the reference from this talk title to this beautiful song, right? Moreover, I think you are here to hear us sing, don't you? Yeah. So, Gabriel, do you want to sing?
No. So yeah, we are actually here to talk about Flow and to give you an introduction into it, what it is, why you should use it or want to use it. We will talk about operators on Flow, how they look like, how they work, threading, which is always an important topic for event streams, and we will finish it off with some useful APIs that you will want to know about if you want to use Flow.
Right, so a little disclaimer, this talk is a little bit more of an advanced talk, and you will see a lot of code on purpose, because we really want you to understand what's going on under the hood to ultimately feel comfortable using it. You will get also the slides in the online somewhere online. We will post it on Twitter to go through the code one by one in case you would like to look up some things afterwards. But to get started, let's take one step back and say we have something very simple like download something from a web server. So we have this function like do an HTTP request that returns an X, whatever X is. Could be a list of something, could be a book, could be anything that you would grab from HTTP server. Like, I think pretty common use case, right? What is the problem with that? So if you are going to execute this, what would happen if you run that directly from, let's say, the activities on create method? What would happen is something like that, right? So app is not responding, or it crashes because you execute network, because you're doing network on main thread. How could we fix that? So we could fix that by surrounding this in a new thread and make it run asynchronously, right? But the next question is like, what do we do once we get the result back? So now we have this X, how do we proceed from there? Okay, on Android, we could wrap it into a runnable and put it on the main thread, on the main looper to get it back to the main thread and execute it then with the result where we manipulate the UI somehow with the result that we got from the backend, right? Another approach would be taking one step back and looking at the method itself. So the method itself is returning an X and is synchronously. What would it take to make this method asynchronously? So we would need something like a callback, right? So we would pass as a parameter to this method, or to this function, a callback. In this case, a simple callback that gets X, which is the result that we load from the backend, and returns unit, in other words, nothing. And once we have it, once we retrieve the X, we would call the callback and make that run in the background thread over here. And then we would call it like that from the main activity or from the activity on create. The problem with that, though, is composition. So what if we have to call a callback? What if we have to do an HTTP request inside an HTTP request, inside an HTTP request, inside an HTTP request? You see where we're going, right? This is also called the callback hell, and JavaScript developers are definitely know what we're talking about here. So let's take one step back again. So we have this callback-based API now. But there is something really neat in Kotlin, right? This coroutines, this suspend keyword. By applying that one, we can do something like that, and magically things work without having this callback hell, right? But have you ever wondered how it works under the hood? So what is the compiler actually doing if we have this suspending function? What the compiler is doing is actually removing the suspending function modifier, or like taking the suspending function modifier and add a parameter for you to this function. So you don't notice it because the compiler is doing it at compile time. But there is something interesting in that idea. So now we have like this continuation object passed in as a parameter to this function that used to be a suspending function. And once we have the result of x, what the compiler does is it adds that line of code that says like continuation.resume. And this is actually the same idea as having the callback before. And Philip Babic, I'm not sure if you attended his talk, but he was also going a little bit more into the details. So in case you haven't, you should check out his talk, which was recorded like any other talk here at droidCon Berlin. But yeah, the idea is the same, right? So we have this callback to somehow tell someone that we have the result now and to make this asynchronously working. Or getting even more generalizing this idea, we could say, instead of callback, we could call it observer. And what we end up with is actually the observer pattern. So let's take this one step further. So we have like this HTTP request, but instead of that, let's move to another example. Now we want to download the video. And not only do we want to download the video, but we would also propagate the progress of how many % of the video has been downloaded yet. Right? So we would like to have something like we download 10%, 20%, 100%. Okay? How would we do that actually with a suspending function? Gabriel?
So suspending functions themselves don't only return a single value. So we can't just do what we did on the slide and add a suspend, and it will magically work like before. So the answer to that is flow, but instead of just putting it there, instead of the question marks, we will take a step back and go there step by step. So this is what we had before. We had the download video function. It takes a callback that has the progress. And we're going to try to make it a bit more general. So first of all, we added downloader added to an interface so we can have reusable implementations of downloaders. Second of all, we are going to make, we cannot just use it for videos, we can do it for other things as well. So we just call it download. We might not just want to emit the progress, so we make it generic, and then we can emit an object that contains other information like download speed or the bytes we received so far. So the downloader itself is very generic now, and but we still have the callback. So let's create an interface for that as well. So it's a download observer. And it needs a function which we can send the data to, which we call emit. And this download observer is then used on top. So for a downloader, this is a super nice generic abstraction, and we're really happy with that. But this isn't actually limited to downloaders. So we could use that for anything that uses the observer pattern. So let's make it this way. So on the left, we will keep the downloader, and on the right, we will transform this to something very generic. So the first step for that is to rename the download function. We will call collect because it collects values that we want to observe. The next step then is to rename the observer to a collector because it receives those values from collect. And now we still have that downloader name in the interface, so we will rename it to Flow, which is our topic. And now the collector will be a flow collector because it collects from the flow. And that's basically flow from the Coroutines library. Oh, well, almost. So there's actually a suspending function, both of them. So we will see later on why this is useful. But this really is Flow and Flow collector like it is in the Coroutines library. We didn't remove any code there. And it's really just that generic observer pattern that we showed in the beginning. So we had this slide earlier, the donut video. We didn't know what to return yet, so we will return a flow now. And how do we actually implement that method? So in the Flow library, there is a builder function. It's also called Flow, but it's not with a capital letter. And it takes a lambda that operates on a flow collector. So if we want to use that, we add equals flow, and then in the lambda, this is a flow collector, so we can call the emit function on the flow collector to actually emit values into the flow. So we emit the first progress and then the other steps.
Right. So now we know how we can construct a flow. Now let's let it flow, right? Let's see how we can actually use that. Switching to yet another example. Let's say we want to emit 5 values and we have like a delay from 100 milliseconds between all of them. So this simple for loop should be really self-explaining, right? What we need actually to make things run is a scope, a coroutine scope. So we put this flow, put it into a coroutine scope and call launch, which actually then launches our coroutine. In the view model, there is like this handy new scope built in with the new beta that is scoping automatically the view model's coroutine scope to view model.onClear, which means once the view model gets destroyed, it automatically clears the whole scope and cancels all the jobs, which means cancels all the coroutines at the end and all the flows in case you have flows inside your view model or inside the scope of the view model. Next, this suspending block here, or the next thing to notice is that this suspending block here is actually then running on a coroutine, which means like now we are in the async world, so to speak. And with emit, we make sure that we are kind of propagating something to the collector, right? So let's remove a little bit now the code of the view model just for the sake of better readability. Let's say we have this, we run this. What do you expect is the outcome of this? Or what would you expect to happen? Well, nothing happens yet, because there's one important thing missing, like the collect. And now we kind of get the values that are emitted above. So let's go once more step by step. So we call collect on it, and this means now we're observing the flow. This means emit, notify the observer, and the observer is the collector, right? So actually, this is how we get one value from above to the collector below. All right?
So as we saw, the flow collector only has that single emit method. And from other reactive libraries, we're used to having an observer which has on error, for example. So how do we handle errors in Flow? As an example, we have this flow builder which just stores an exception. And what will happen? The collect will actually rethrow that exception, and then you can handle the error like you would handle any other exception you usually handle with a try catch around it, and then in the catch block you can just write your error handling. In general, though, we would recommend to not do this and just make errors part of your stream. So if we have like this example, which is similar to the donut example, it emits some progress and then just throws in an error for some reason. So we would model it something like this. You would create a sealed class, which is donut status. Then it would have subclasses for progress, success, error. And then inside your flow, you would first emit the progress. And then when the exception happens, you would catch it inside and then just emit the error. And then in the end, in collect, you handle errors like you would handle regular progress or success updates. The other thing that's usually in observers in the Rx world is on complete, which also is not here. So how do we handle completion? When we have some flow that's launched, It starts a coroutine, which then will execute the flow method, which creates the flow. Then it goes to the next one. It will call collect. And then at the end here, it will suspend and wait. In the meantime, a second coroutine will run and will actually execute the inner parts of the flow. So the do stuff, whatever it does, will get executed. And then when it emits something, the lambda from the collect will be called, and that will go on until do stuff is done. And then the inner coroutine is done as well, so the first coroutine will stop suspending, which means our incomplete code can just go after the collect. And that's it. In the latest version, in 1.3 milestone 2, there's also an onCompletion operator, which is similar to do onComplete from RxJava, which lets you do completion handling inside the stream if you prefer that style of declarative programming.
Okay, next let's take a look how an operator can be implemented. So now we're going to implement the map operator, which is, I think everyone who has used the Kotlin standard library, or most of us have already used this operator. It's like mapping a value to another value. All those operators are already part of the Flow library itself, but for the sake of getting really understanding what's going on, we're going to re-implement map now. All right? So let's get started. So taking our example from before, what we want to do now is we still have this flow that emits every 100 milliseconds one value, and we want to map it in terms of what we are doing is we are just multiplying it by 2, and then the collect at the end gets like the multiplied value. Okay? All right, so let's take one step. Let's take step by step now into what's going on under the hood. First, let's start with actually we use another concept of Kotlin, which is extension functions. So please note that now we are going to introduce a map function on the type flow. Okay? So all operators in Flow are actually extension functions. That's really what's happening in the library. Also, let's take a look at the transformer, which is the parameter that we get. So we get a value of t, and we return a value of r. In the example that we do, we are basically mapping from integer to integer, but we could map from integer to string or any other type, right? And most important, we also return a flow. Okay? We return a flow of r, where r is like the result of the mapping, the type of the mapping result. So how do we get started writing this operator? So next step, as we already know, we can create a flow by using this flow builder. And I want to highlight and leave the brackets in blue here because it's getting a little bit complicated, or not really complicated, but harder to read as we go on. But this is now, like inside this blue bracket, this means flow collector. Okay? Just keep that in mind. I will highlight it later once we need it again. So what we do next is we want to subscribe to something or observe something, so we call collect. And collect is exactly the same thing that Gabriel has shown before. It's like the flow collector.collect method that we can call. Flow.collect. And this collect is referencing to the flow. And since it's an extension function, you may wonder, but which flow? So going back to the example that we gave, that we showed you before, flow means the flow that gets returned from this blue lines. So we are actually calling collect on that flow returned by this builder, like the for loop. All right? So the question is, how do we get the value from here to the next thing? Yeah, it's exactly calling collect. Collect is doing that. And emit is kind of pushing it, and collect is receiving it. That's why inside the map function, the map operator that we're going to write now, we call collect, and we get the value. In other words, we subscribe to this for builder, that was the first part of this example, inside the second part, which is the map function. All right? Next, what we have to do is basically calling the transformer with the value that we get. So we get like the value 1, we call the transformer with it, we get 1 multiplied by 2 out of it, and that is R. And what we do now is we have to push this value down to the next thing in our chain, which would be then the collect that just prints out the value. And how we do that? By calling emit. And emit is now the function that also Gabriel showed before that is part of the flow collector interface. So this is literally flow. It's just these two interfaces, which allows us to collect something and to emit something. And this is how we push the value from here to the next thing in the chain, which is the collect itself, where we just print it. So operators are still just observer patterns. So there's no difference between what we have heard before, how we observe things, and operator. They are the same in terms of the same idea. To getting a slightly more complicated example, who knows what switch map is? Please raise your hand. All right, quite a couple of people. Just to give you an example what it does, or what it would output is, switch map, instead of, in contrast to a flat map, would cancel any ongoing transformation or job once you get a new value emitted. So in the middle of this example, we see switch map, and we create there a new flow. And whenever we get the value 1 from upstream, it will start a new flow, and it will print out first value 0, and then it will wait 500 milliseconds. In the meantime, we get from upstream another value 2, and this one will now cancel the previous flow. That's why we don't see any second value as output in this black box, which represents the outputted value. Okay, so this is kind of switch map. Let's see how we can implement this. So again, switch map is already part of this standard library, just for the sake of demonstration, and I'm going to re-implement this again with you. So this is our method signature, right? So we have similar things like we have shown before with map. We have it as an extension function. We get this mapper, but now the mapper returns a flow of R instead of just R. That's the main difference to notice now. How do we create a flow? Well, again, we use this flow builder. We have to call collect to subscribe to whatever comes from upstream. And now, well, like we have the value from upstream. What do we do with that value? Well, we have to pass this value somehow downstream, right? So we only have focused now, again, on what's coming from upstream. But the question is, how do we pass that value from here downstream? So in other words, what we have to do is now get the new flowable that is inside the switch map by calling this mapper function. And now we have a flow of type R. And now we have to subscribe to this new inner flow. Okay? So I know it's getting a little bit complicated, so you probably would like to check it out later again on your own in the slides that we are going to publish. But what we do now is we have this inner flow that got created from this mapper function, and now we are subscribing to it to get the values out of this. And now, as a next step, first we have to launch it, because otherwise it wouldn't start, right? Because it's a new flow, it's a new kind of thing. So we have to launch this new thing by calling launch, which then starts a new coroutine. And now that we have the value, we can emit it. And emit now refers to the flow collector, the blue one from the parent, so to speak. Does it work yet? Not fully. We are almost there. So now, if we would leave it like that, we would have basically a flat map, because we never cancel it whenever a new value comes in. To cancel whenever a new value comes in, we kind of have to track the job from this inner flow. So we take this inner flow, save it into, we call launch on it. Launch returns a job. We save this job into a variable, and whenever we get a new value in, it's as easy as call cancel on the previous job, if there is any previous job. There is one more thing that is important, which is we also have to, or we only can call launch inside a scope. That's why we have to create a new scope. By calling this method Coroutine Scope, we basically create a new scope by taking whatever the parent scope is right now. And then we can call launch. And this is switch map, and there is nothing simplified. Also before in the map, there was nothing simplified. It's really that piece of code that is also actually baked in the flow library, more or less. Like the map is pretty much one-to-one. The channel, the switch map is a little bit more simplified here, but it is working like this compiles and works. In the Flow library itself, it's probably a little bit more optimized by using some more synchronizations mechanism and stuff like that inside. But the main idea is still the same, and that would also work perfectly well.
So let's take a look at threading. But before we can do that, we will actually need to take a look at two concepts from the Coroutine library, which we saw already to some degree. The first one is the coroutine context. A coroutine context consists of multiple elements, which are also coroutine contexts themselves. We will take a look at two of them, because those are the most common ones and the ones that are most relevant for us right now. The first one is job. We just saw a job. It was used to cancel the inner coroutine, and that's the main use case for us now. It does a lot more internally and for coroutines themselves, but we will just ignore that here. The other context is the coroutine dispatcher. It basically is like a scheduler in RxJava. It determines where your coroutine runs. The library has a bunch of dispatchers baked in. So there's a main dispatcher, which runs on Android on the main thread. There's a default dispatcher, which is a thread pool. And that dispatcher is used by default if you don't have any other dispatcher specified in your context. And then there's some more like I/O, which is a thread pool for blocking work, or the new single thread context, which just gives you a new thread. And as I said, a context consists of multiple elements, so you can just combine multiple ones with a plus operator. And that's usually what you see. You have a job to cancel the context and a dispatcher to determine where it's executed. The second context, the second concept is the coroutine scope. It basically just holds a reference to a context, and that's the interface itself. It has a bunch of extension methods on it. So for example, there's cancel, which will then just cancel the job inside the context of the scope. And the other one is launch, which we already saw. There are two baked-in scopes already in the Android X KTX libraries. There's view model scope, which Hannes already showed. It uses the main dispatcher and a job that gets canceled in onCleared of the view model. And the other one is on lifecycle, which also uses the main dispatcher, but it gets canceled in the onDestroy of the lifecycle. So let's look actually at threading. We have in scope on the lifecycle, we use launch when started, which is similar to the regular launch, but it will only get executed once your lifecycle reaches on start. And then we have a flow inside. It will just do some expensive operation, emit ints. Then the first map will increase the int by 1. Then we will convert it to string in another map, and in the end we will print it out. So where does all of this run? Like I said, Coroutine Scope uses the main thread, so that's probably involved. And indeed, the print will run on the main thread. The maps will also be executed on the main thread. And since we're not doing anything, the expensive operation as well, which is kind of what we don't want, and the anti-pattern we showed in the very beginning of this talk. So how do we get off the main thread here? One example would be to just use a different scope that has a different context, so it runs on another thread. So for example, global scope always has a different context, and we could emit there. And we get off the main thread and observe it there, in theory. Another way would be with context. It's a coroutine method that just lets you switch the context you're currently in. The problem with both of those is that it will actually result in an illegal state exception when you call emit, because Flow has this constraint that your emissions have to be done on the same thread or the same context as the one you were called on. So we cannot change we cannot emit on a different context, and we cannot influence the context of the downstream. So we cannot actually do anything in here directly to get off the main thread, at least not directly. So one way to actually do it would be a different builder. It's called channel flow. Internally, that one uses a channel. This, in this case, is not a flow collector, but it is a producer scope, which comes from Coroutine Channels. And instead of emit, you call send. What happens internally is that the channel then will switch context from the I/O context you're in right now when you call send to the original context, which would be the main context, and then call emit there. So in the end, the main thread would still be there for the maps and the collect, but the lambda inside the with context would be executed on the main thread, so we achieved what we want. This is not what you would usually do, though, or not encounter that often in the real world, because usually you just get a flow from somewhere, like from a database, and you want to observe it, and you don't actually control the builder. So how would you do that? Still the same example. There's an operator called flow on, and we'll call it with the I/O dispatcher. So what will this look like? We have I/O thread now and the main thread still. Println and the lower map will still be on the main thread because flow on is above it. And like I said before, you can't actually change where downstream emissions happen. So there's nothing like RxJava's observe on. And you couldn't even implement it if you would want to. And then the upper map and the expensive operation would be executed on the I/O thread. Then if we take the example again and just add another flow on to make it a bit more interesting and have 3 different contexts, now we have default below the first map and I/O for the flow on. So that's what it will actually do. So map will be called on, the lower map will be still called on the main thread as well as the print. The upper map will be called on the default context, and the expensive operation still on the I/O thread. So in summary, the collect lambda is guaranteed to be always called on the context of your scope that you launched it in initially. So you will never run into the problem like you do sometimes in RxJava, where you get an observable and you don't really know where is it executed on. Do I need to add an observe on? You are 100% sure it will be run, your code will be run in your context unless you actually add a flow on. And the flow on will only influence the upstream. So it's also not like subscribe on, which will, when there's no other operator like observe on later on, will go up and then down again. And the third thing for the summary is really nothing can change the context of a downstream emission.
So next, some useful APIs that you might find useful in your daily work, now that you feel comfortable with all this context and flow and stuff like that, right? So let's see how we can use it in our daily work. We can use something like flow off, which is similar to RxJava's just or something like that, right? So if you would create a flowable that emits 1, 2, 3, 4, that's what you can use for. Or you can use create just a list and call an extension function as flow on it. Or the same thing for a sequence. You can also convert functions like this one to a flowable or a suspending function. There were also packages, or there's an additional artifact or an additional package that helps you convert from RxJava to Flow and vice versa. So if you have like an observable from RxJava, You can convert it to a flow by calling as-flow on it. And the other way around, you don't have to take like one step in between, which is calling as-publisher, which transforms to a Flowable from RxJava, which is implementing the publisher interface, which is one of the reactive stream specifications interfaces. And then you can call to Observable on it, which is part of the Flow library, or if there's additional Flow to RxJava library. There are also a lot of operators that you already are familiar with if you're using RxJava. So for instance, subjects are still there kind of in the Flow library by using channels or channels.asFlow to get a flow out of it. FlatMap FlatMap from RxJava is there in flows. It's just called FlatMap merge. ConcatMap is called FlatMap concat. SwitchMap is still called SwitchMap, so that's the same. And some other usable operators are there as well, like map, filter, retry, zip, combine latest, take, scan, reduce, and a bunch of others that I didn't put over on that slide. But more or less, the most common ones are also available on Flow, or the most common ones from RxJava are available also on Flow. One other example, or real-world example, would be to make something like an HTTP request. And in RxJava, you would use something like a single. But in the Coroutines or Kotlin world, you have this convenient suspend thing, right? And with Retrofit 2.60, you have built-in support for suspending function as well. So now that we have this suspending function to get a book, the favorite book of the user, let's see how we can use it in a flow. So let's say we have a flow that emits 2 times the ID of the user. So what we would like to do is like, grab now the book of the first user and print it out. So we have something like the sum operator, and we will see what the sum operator is in a second. But what we would like to have is something like that. We just call this get favorite book, right? We get the book back, and then we just print it out or do whatever we want to do with the book. The question, what is the sum operator? Any guess? So how would you do that in RxJava? In RxJava, you would have like a single, and you would have to flat map a single into an observable or something like that, right? With Flow, it's just a map. Why? Because map, or the lambda that you pass to the map, is a suspending function, and suspending function can call suspending function. So no flat mapping required or something like that to achieve exactly what we want. So to sum it up, Flow is like this RxJava equivalent to event streams, but it's baked on coroutines, which also adds a lot of other nice benefits, like writing an operator, as you've seen before. All right, the switch map was probably a little bit complicated, but the map operator, I think that is something that feels natural, also by using these builders and stuff like that. RxJava is working quite similar under the hood. So it's exactly the same idea of an observer pattern. And you observe something from upstreams to get the value somewhere below, and then you call something from the next observer to get like this chain working. That's still the same thing. Some other benefits that you get out from coroutines is like backpressure, which we didn't cover fully yet in this talk, and we don't have time to do that. But with the design of coroutines and suspending function, there is already backpressure baked in. So that is nothing that you have to do inside your code as an author of an operator, for example. Whereas in RxJava, you do have to confirm to a certain protocol and so on. So this is kind of a little bit easier to write when you compare writing operators in RxJava versus writing operators with Flow. And that's basically it. So now that we have 1 or 2 more minutes, do you want to sing us that song now?
Yeah, still not really.
Okay, but we would take some more questions in case you have some questions. There are some microphones.